extreme tolerances, impossibly smooth surfaces, and machines that operate at the edge of physics. Welcome to Holroyd, where ultra-precision isn't a claim, it's a standard. The process begins with massive rotor blanks clamped into position. These components, used in air and refrigeration compressors, demand accuracy within microns. Milling starts with rough cuts for heavy stock removal. Their 8EX rotor production centers are built for this, combining high power and rigidity for consistent results. An advanced cutting head with an extra axis of movement follows complex profiles, preparing the part for finishing. Even the initial setup is simulated in advance to eliminate margin for error. Coolant systems are optimized to prevent thermal deformation during long operations. At this stage, surface quality and form are everything. Flexible tooling adapts to the exact geometry of the component, guided by CNC controls that make adjustments in real time. In-process sensors constantly track tool wear, feeding live data to the controller. If tolerances drift even slightly, the machine compensates automatically. Precision never sleeps. Next, it's over to grinding. Wheels made of dressable aluminum oxide, or CBN, are profiled for micron-level precision. The grinder isn't just removing material, it's sculpting the part to perfection. The maximum size? 420 millimeters in diameter and 2.2 meters long. This isn't heavy industry as usual, it's mechanical craftsmanship at its finest. After machining, each component undergoes inspection. Hand finishing follows, with expert technicians refining areas where no tool can reach. Holroyd doesn't just build components, they also build the machines that build them. And when those machines wear out, they bring them back better than new. This is engineering pushed to the limit, built for aerospace, refrigeration, and high-performance industrial use. Every rotor, every surface, every micron matters. At voestalpine, heavy steel machinery gave way to newer giants, and engineering performance as precise as it is powerful. This is no routine maintenance. It's a leap from 160-ton to 180-ton LD converters, supporting a production boost from 5.4 to 6 million tons per year. First, the old converters were carefully disconnected, gas lines sealed, electrical systems isolated, and protective works erected. Heavy-duty cranes lifted the 160-ton units out, inch by inch, amid a symphony of hydraulic hiss and controlled tension. Then, the new 180-ton vessels arrived. They were aligned on-site with laser-guided frames, precision within millimeters. Engineers fitted advanced trunnion rings and a suspension system designed to absorb thermal expansion. The converter's geometry was matched with custom-built supports to ensure perfect load transfer. Multiple teams worked in shifts, around the clock, to keep downtime minimal. Next, slag shields and bottom stirring devices were installed. Every weld, every bolt torqued to spec, was verified through pressure and leak testing. No guesswork allowed. The installation of an air cooling system around the converter shell lowered operating temperature and extended equipment life. Advanced diagnostics were used during commissioning to monitor stress and performance in real time. No shortcut, no compromise, just methodical progress under high stakes. Once assembled, final checks began, rotating the converter, testing sublance movement, and verifying slag handling pathways. Control systems were integrated and mapped to Pre-Metal's automation platform. Only after every parameter passed rigorous inspection did they power up the first heat. What followed? A triumph. 3 bigger converters now stand ready, built not just for capacity, but longevity. This is heavy industry refined, where raw tonnage meets surgical precision. Every weld, sensor, and steel plate is part of a wider strategy, stronger capacity, longer runtime, and operational excellence. Precision under pressure. That's what defines the making of a carbon composite cylinder, and every step here is engineered for performance. This is where strength meets safety. Inside Luxfer's facility, carbon composite cylinders take shape under one of the most sophisticated manufacturing processes in the industry. It all starts with a flat aluminum disc. Through a deep draw process, it's transformed into a seamless cup that becomes the cylinder's inner liner. Each liner is washed and visually inspected for imperfections before moving to the next step. Then comes liner spinning. The metal is stretched and shaped using a mandrel to achieve uniform wall thickness and precise geometry. Afterward, heat treatment strengthens the structure, preparing it for the machining stage. Ports are cut and threaded with exact tolerance. Every dimension is verified. No shortcuts, no guesswork. Each liner then undergoes a detailed inspection before it's ready for composite layering. Now the real magic begins. Carbon fiber is tightly wrapped around the liner in multiple orientations. This composite shell adds incredible strength while reducing weight. A label is applied, and the wrapped cylinder is cured in a controlled environment. After curing, the surface is sanded for uniformity. Then comes hydrotesting, pressurizing the cylinder to confirm structural integrity. Each test isn't just a checkpoint, it's a promise of reliability. Failure is never an option when lives depend on containment. Finally, a UV-resistant gel coating is applied to guard against light damage. One last inspection confirms that the cylinder meets every safety and performance benchmark. This isn't just a product, it's pressure containment perfected.
I can take this anymore. I might just break all the way hard and ache, 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 all the way hard and ache.
Steel bars, sparks flying, and an entire line synchronized like a machine orchestra. This is how engine valves are made, with precision, heat, and timing that leave no room for error. At Varric's facility, it all begins with bar shearing. Long metal bars are cut into uniform lengths, the starting point for each valve. Next is friction welding, joining the stem and head portions by spinning and pressing them together until they fuse without melting. It's clean, fast, and strong. The semi-finished valve then undergoes upset forging. A powerful ram compresses the head area, giving it its recognizable mushroom shape. From there, it enters a continuous furnace, where heat treatment improves material strength and fatigue resistance. Now, the real refinement starts. The valve seat receives a deposit layer to ensure durability. In the machining area, bowl feeders automatically load the parts into the line. Rough end grinding removes excess material, setting the baseline dimensions. Profile turning follows, shaping the valve's body to final form with CNC-guided precision. Then comes groove grinding, adding the locking feature that holds the valve in place during engine operation. Each valve head is then turned to the correct diameter and faced to a mirror finish. Induction hardening strengthens the stem end. Finish end grinding achieves the final length and smoothness. At this point, every dimension must fall within microns. There's no margin for guesswork. The entire process is timed down to seconds. No wasted motion, no unnecessary steps. A separate quality station checks concentricity and straightness at multiple points. Even the slightest deviation is flagged and corrected before moving forward. Seat grinding ensures a perfect fit, where the valve seals the combustion chamber. Another induction hardening process targets the seat for extra wear resistance. A flash of chrome plating is added, thin but essential, to reduce friction and corrosion. Each valve then passes through a final surface finish stage for cosmetic consistency. It's the finishing touch on a component that has already passed a dozen precision milestones. Before packaging, every valve undergoes automated inspection. Sensors check for dimensional accuracy and surface defects. Only flawless parts make it through. What you're watching isn't just parts being made. It's control, consistency, and commitment at scale. Each valve carries the responsibility of performance, heat resistance, and trust. Stainless steel bottles don't shine on their own. This is how the polish is perfected. At Sun Glory, outer surface finishing is a CNC-controlled dance of precision and motion. Each bottle is secured on a rotating spindle, moving under polishing wheels with satin or mirror-grade abrasives. The system runs on PLC with servo motors, ensuring tight tolerances of plus or minus 0.1 millimeters. At 180 pieces per hour, the entire cycle moves like clockwork, fast, clean, and consistent. Operators load raw bottles, and within seconds, matte textures or high-gloss finishes emerge. Even small imperfections are targeted. This isn't just polishing, it's surface engineering. The machine adapts to various products: flasks, tumblers, coffee pots, all shaped to consumer demand. With just 2.2 kilowatts of power, it achieves impressive throughput while keeping energy use minimal. Before exiting, each bottle is visually inspected. Whether satin or mirror finish, the result is sleek, uniform, and ready for final assembly. This is where steel gets its shine: beautiful, industrial, and engineered to last. No mercy, no delay. This is the last stop for every machine. At 109 U-Pullet, cars meet their final chapter under the jaws of the engine biter and the car crusher. The process starts with vehicles stripped of reusable parts. What's left is pure metal, and that's when the engine biter steps in. Its claw grips the frame, while hydraulic arms twist and rip the engine straight out of the bay. It's violent, fast, and brutally efficient. You can almost feel the torque in every tear. It's mechanical carnage with purpose. Next, the stripped chassis rolls onto the car crusher. Massive steel plates descend with unstoppable force, flattening the car into a thin slab. There's no turning back once the crusher begins. Only compressed steel remains. This isn't just destruction. It's preparation for recycling. The compacted metal is easier to store, transport, and later melt down into raw material. Every crushed shell becomes part of a sustainable loop. Less waste, more reuse. This is scrapyard engineering. Loud, rough, and surprisingly precise. Steel this thick isn't easy to bend, but that's exactly what happens here. At Faxen, massive S460 steel plates, up to 180 millimeters thick, are transformed into XXL monopiles using their advanced 4 Hell XL 700 WT4 roll plate rolling machine. The process begins with feeding and aligning plates on a motorized table. The system performs 2 pre-bending passes, reducing flat spots. Then, full rolling begins, precisely shaping the plate with CNC-controlled rolls. Each rotation is fast, smooth, and consistent, ensuring tight tolerances and minimal waste. The Siemens-controlled HMI allows real-time adjustment, even wirelessly. The entire setup is built for power, up to 700 tons of pressing force per roll. Despite the scale, every movement is coordinated like clockwork. Plate ejection is automatic, and the results? Near perfect roundness. Every weld-ready cylinder supports offshore wind turbines, built for strength and durability in harsh ocean conditions. Fire and metal, locked in motion. The heartbeat of heavy industry. This is Pilson steel, where raw ore becomes engineered strength. A massive arc furnace blasts electric current into scrap and pig iron, melting it into liquid steel. Once the right chemistry is achieved, the molten mix is tapped and poured into ingot molds. You can almost hear the hiss as metal meets cooler steel. These glowing ingots are transferred to forging presses. With thunderous hammering, they're compressed, elongated, and refined, removing internal voids and aligning grain structure. Each blow shapes not just metal, but the material's integrity, control with every ton of force. Then comes machining. Forged blocks are drilled, milled, and turned to precise dimensions. CNC cutters carve patterns, the hidden details that define real-world performance. Finished parts are cleaned and prepared for dispatch. It's not just a process. It's discipline, precision, and repetition honed over decades. Every step is a dialogue between material and machine, each responding to the other in perfect rhythm. Watching this process feels like observing steel undergo a transformation from chaos to order. Pure craft at industrial scale. In the pattern-making shop, wooden and resin patterns are carefully carved for sand casting. Molds come together in matching halves, forming cavities that replicate final components. Molten steel is poured, filling every crevice. After cooling, the cast parts are freed from sand and flash. Heat treatment follows, heating and controlled cooling to achieve specific hardness and toughness. Inspectors measure hardness, grain flow, and dimensional accuracy, making sure every piece is built to spec. Finally, parts are finished, ground, buffed, and coated. Each unit is cleaned and labeled before shipment. Boxes are packed, paperwork sorted, and trucks arrive. This is more than production. It's fulfillment in motion. From glowing ingot to ready-to-install component, Pilson steel covers it all, making molds, forging shapes, machining parts, and casting components in-house. This isn't just a factory tour. It's a lesson in metallurgy and mechanical engineering, in process synergy and purpose-driven craftsmanship. When you see a steel beam or machinery part, know there was a journey of heat, force, and countless hands behind its creation. This is Pilson steel's legacy, turning raw elements into engineered reliability, ready to stand decades under pressure. At Ethos Energy's facility in Rayong, Thailand, worn gas turbine components are brought back to life with industrial precision. Each part begins with hydrogen fluoride cleaning and detailed material analysis. Technicians verify metallurgical properties and coatings before any machining starts. CNC tools reshape worn areas. Automated shot peening restores surface strength, while EDM drilling reopens clogged cooling holes with micron-level accuracy. Repairs are scheduled in overlapping shifts. Work never stops because downtime is costly. Welding operations take place in controlled atmospheric chambers, including elevated temperature processes for transient phase restoration. Vacuum heat treatment follows to restore original material properties. Then comes the surface protection. Robotic thermal spraying applies air plasma or HVOF coatings. Every component undergoes 360 degrees inspection. Pulse thermography, FPI, CMM measurement, and flow testing ensure structural and thermal integrity. This isn't just repair, it's technical resurrection. Before leaving, parts are assembled and checked for turbine fit and clearance. In a world where turbines can't fail, every micron matters. Blazing heat, swirling gas, and mountains of scrap. This is how copper anodes begin. At the Horn smelter, over 740,000 tons of copper-bearing material arrive annually, containing anywhere from 10% to 40% copper. After material receiving and sampling, the feed enters a specialized reactor. Here, gas phase sulfur is released while impurities like iron and silica are drawn into the slag, still holding about 4% copper. What remains is matte, enriched to 70% copper. It's then sent to the Noranda converter, where oxidation transforms it into white metal. This crucial step drives off remaining sulfur and boosts purity. Next, it's transferred into the concentrator and then back into another reactor for final refining, still maintaining 70% copper content, but with reduced contaminants. The result? Copper anodes at 99.1% purity, ready for use across industries, from automotive to food processing, and even pharmaceuticals. This process is loud, hot, and chemically intense, but it's also controlled, deliberate, and vital to global copper supply. Steel doesn't bend easily unless you know exactly how to push it. At this facility, pipes, beams, and structural steel are bent into precise arcs using massive rollers and hydraulic power. Each setup is tailored to the material. Round tubes, square profiles, and I-beams all require different dies and force settings. Operators adjust pressure and speed in real time to avoid kinks, wrinkles, or deformation. And the finish? Curves that look right and hold strong. Whether it's for architecture, transport, or industry, every curve must match exact specs, because in steel bending, precision isn't optional.